Good afternoon to all. Now we will see on the neural network part 2B we call it, on the inverse modeling where we'll be using it for the control strategies. And if you've seen the previous slides on the steps for the forward modeling, now on the inverse modeling, it's just basically the same, more or less the same steps you have to follow. Seven basic steps. The only issue is the input and output pattern will be different in this case. Basically, again, we talk about this dynamic state modeling. When we talk about the inverse modeling, we are basically looking into the dynamic part. Okay, the steady state part. Also, we can have inverse modeling, not issue, but we will more be using it for the dynamic state modeling because at the end of the day, we would like to use it for our control strategy. So we define this dynamic state modeling for the inverse models. What does it mean? It means to predict the present manipulated input with presentation of past and present system inputs and outputs together with the set point into the neural network structure. Okay, so the input must consist of past and present inputs and outputs and the set point, of course, which is actually the future output that we've seen in the modeling side. We have the yk plus 1, the one that we are predicting in the future, the next step. So that would be basically the set point for our inverse modeling that is to be used for the controls. To predict what? To predict the manipulated input, the U basically, so that we can put it into our control strategy. Okay, at the end of the day, our main aim is to use it for control strategies for inverse modeling. So we definitely would like to have the manipulated input, which we call U at K, present time, of course. We would like it to get the present U as the manipulated input to be used in the control system to achieve the set point that we would like to obtain. For inverse modeling, we have two configurations. We call it, one is the open loop or general method in the terminology of neural network methods, and or the specialized method, basically the closed loop in our control strategies or modeling strategy, which is called the open closed loop in the neural network text, or literature they call it the general method or the specialized method. And basically this inverse model can then be used as controllers for different strategies. Depending on what strategies you use, we can put it in the inverse model as and when necessary. Okay, in the generalized method, it's similar to like the forward modeling, except the inputs and outputs are different. So we have the system model that we want to map, get the to predict. Okay, so we predict the yk plus 1 in this normal model. So to get the inverse model using generalized method, basically we are putting the past in past y's, and the present one. The present one is the yk plus 1, which is basically going to be the set point. When we introduce into the control strategy, this will be the set point, but now it's just the modeling part, not the control part. So we don't call it as a set point, we call it as a y prediction. I predicted at k plus 1 together with the inputs at the past. These are the z minus 1 means are the delayed values or the past values that is inputted into the neural network to get the u, the manipulated input. And this is compared with the actual u that we like to have. And this error is used to train the neural net. Training means to get the best basically weights. After we have decided on the structure, we follow the 7 steps and so on. Then we go to the training signal using backpropagation method or any other different methods that they have in the market now to train to get the U. So because the optimization method will go to until we get the error to the error that we want, and then we get the neural network that is required for our if you want to use it for control, for the control. So this is the inverse model that is obtained using the generalized method, as we call it. So it's more like an open loop system because it's the input output structure that we've seen in the forward model. It's the same as the forward model. Only thing now this YK becomes the input and this UK becomes the output. While the forward model, the UKs and all these are inputs, plus the UK's input, the output is YK plus 1. So we just inverse it. This is called the inverse model using the generalized method we call it. And the specialized method, which is closed loop. See, it's on a closed loop system. Same thing here. The inputs are also the pass U, delete U's, the pass Y's, okay, and also we have the YK coming in is the input, okay, and the output is the output of this mod of the neural network is the output. Again, the U is the output, the manual is the output, but it goes to the model of the system to give the YK and use this YK plus 1 compare it with whatever YK we want at that point to train the neural network. So this is closed loop because it's like already implemented as a controller. This is like the controller, and this is the system. As we know, the perfect controller is the inverse of the model of the system. So this is already like a controller. Train it in this way, but the only thing, the error is not the U. The error is the YK plus 1 that has gone through the model of the system compared with the actual one that we want, and this error is used to train to get the best neural network. Okay, the only difference is that the U is not the direct error propagation, it goes to the model system. So when we train the neural network using the back propagation, we have to slightly modify it to cater for also the gradient for change between U and YK. The gradient in the system has to be incorporated in the training algorithm so that it is trained based on whatever YK it is, not on U but on YK. So this is basically a closed loop specialized method because it's trained as though it's going to be used, and it's way more practical, okay, more you can say closed loop, and more should be more stable in most cases, depending on how you train it, and implemented in the as an inverse model as a controller in whatever system that you want to use it for. So these two methods, open loop, can be used in all these different control strategies that we have for neural network. We have many other different brands, but these are the main basic ones, basically the predictive methods that we use a lot of times. We want to use the indirect adaptive control method. You can use it directly as a direct inverse control method, okay, or we can use the internal model control method, which is more or less like direct inverse, but you have another forward model in parallel with the model of the system to be used in what we call the IMC method. But these are the basic control strategies that we can use neural network either as a model itself or as a inverse model or both together, using neural network in these different control strategies methods. But the main thing is to get the neural network trained on the inverse models most of the time. But if you are using it as a model, then you have to train it based on the forward model that we have studied in the last talk, the last slide or last lecture on the forward model. That's for the forward model. If we inverse it, we have to use this method. So you want to use both, you can use that model and this model. It depends on how the strategies that you want to implement the neural network on in the AI control methods. So if you use the predictive control method, it's basically using the neural network model part, the forward model, using the pass input, pass outputs, and so pass inputs, pass outputs to get the YK and plus n, YK plus n, the predicted Y's, okay, and goes through the non-linear optimizer, and so you can implement in the MPC method, MPC model, and so on. Okay, this is one way of implementing neural network inside the control strategy. You don't really need the inverse model because you're basically using a forward model. The inverse, the controller is done using an optimizer itself. Okay. But if you need optimizer to use the neural network model, you can use the neural network within the optimizer. If not, you can use the first principle, depending on how you plan the strategy. Okay, that's direct adaptive control method okay, where in this case basically you are using the forward model, okay, the pass inputs and the pass output of the system. Okay, it can be from the plant, it can be also from the neural network, depending how you look at it. And you train the neural network, put a emulator or the model here, and so you have a reference model E2 also as a check, but also you have a neural network controller, which is the inverse model itself, to be used as within the strategy. Okay, here you are using the controller, but you are also using the emulator where this is being trained, and this is the adaptive part. That is continuously being adapted, being trained, being updated to be able to cater for disturbance and so on. And then as it goes along, it goes check on the reference model. If not, we keep on training, or we can also adapt this if you want. We can have another strategy to adapt it. But in this case, we have an indirect. This is an indirect adaptive. It's not directly adapting the controller. Indirectly, it's adaptive. If you want a direct adaptive, you can also adapt the neural controller directly. It depends on how you plan your strategy. But this is where you can use neural network as an in adaptive control. Adaptive, a lot of strategies you can use. This is one common way, and there are many other ways of using a neural network. Adaptive. Adaptive means you're adapting it all the time, depending on the changes that you encounter in the control performance or control strategy for the system. And this is when you directly in use. We call it direct inverse control method, because the one that you trained just now using your general method, the open loop method, okay, or if you use the closed loop specialized methods, okay, you have trained it before with the same inputs output, put it inside the controller as a controller, and it will be sending out the manipulate wave to control the planet system, okay, using whatever set point that you want. You have trained it on the set point, you implement it straight away like this. And as I said before, in the real world, the controller is just an inverse of the model. A perfect controller is the perfect inverse model of the planar system. You have the perfect inverse model of the planar system, you will get a perfect controller. So the better your inverse model, the better your training of your inverse model, the more accurate your inverse model, then more accurate controller you're going to have in your system. Okay, of course you have disturbance and so on. You can use adaptive, or you can use the next method we see to adapt for that. But if you have a very straightforward system, very little disturbance, very little noise, then you can implement this with the controller directly into the controller itself. This is the same thing, but you have a IMC for the IMC method, where you also have the forward model running in parallel with the planar system. Forward model coming in, compare with the set point, the E is sent into the number, you still have a filter to be able to slightly improve on the performance of U and so on. You can have a filter if you need to, and you implement this using the inverse model controller, whether you use the generalized method, or the specialized method to get the inverse controller, doesn't matter, but that can be implemented here as the neural network inverse model controller. This forward model using the method of the forward modeling method that we studied in the last lecture I've seen before. Okay, so it's implemented as an IMC to cater for disturbance and things like that. This is a much more better method than the previous method, which can be quite difficult for disturbances and so on. But in this case, we'll cater for the disturbances by the forward model, and the error is taken care of. This. So all this is different strategies that we can use neural network. This is the two ones before, the number 3, number 4. The more ones directly using the inverse model. Whatever it is, all this they still have to go to the 7 steps that we studied before to propagate the data, the input-output pattern, the excitation, the data set, training, all that have to go through. Okay, the same as the forward, you also use the same thing, the same strategies for the forward model, you also use the same strategy for the inverse model. Only thing, the input-output pattern is different. That's the main thing. Input-output pattern for this slightly different from the input-output pattern of the inverse model. But the strategies to obtain the neural model will have to follow very closely to be able to get an accurate model, so that we get an accurate controller. The most important here is the controller. If this controller is not accurate, not done properly, then you'll have problems in implementing it as a control strategy, and it will not work. It will not be robust. It may work for certain period, for certain things, for certain position. It will not work. Certain condition, it will work. For certain condition, it may not work because your system has not been robust, because you have not trained it on enough data set, or not the right excitation signal, and especially when you're dealing with non-linear system. These are mainly for non-linear systems. You may mentioned before. For linear systems, we've got the PID to always work on it to work, but for non-linear systems, it's difficult. We need to implement these advanced methods, and AI method one of them, and all depends on how good you get your controller, and how good the controller depends on the steps that you follow in obtaining the models for the forward model or the inverse model. But since this is a controller, the inverse model or the controller becomes more important. It is the main criteria for making this whole control strategy work properly for us. Once the neural network models obtained offline, they can then be implemented in these various control strategies for the servo, okay, the set point change, and the regulatory control for disturbance changes, and as well as for other robustness tests. Make more robust when you implement noise. Okay, you implement plant model mismatch. It's always good to have all this as a typical strategy that you need to use to test any controller. Is the servo, the set point, and also with disturbance, and also with other noise and blast, to make sure that your controller that you implement, whether be AI or any control, is robust and can cater for any disturbances or changes in the plant as you implement it online. Okay, since these are all obtained offline, so you're doing it online, so you must make sure it's robust. You can have an adaptive controller that are implemented, not for all systems. Some may be easy, some may be difficult, but you can implement. But whatever it is, offline train must be as accurate as possible, so that when you implement it online, you will not have problem with robustness. At least close to the operating region. If it's very far away, out of the training region, it's not surprising if it doesn't work. But if it's within the training region, within the training data, within the data set that you have, that you expect the controller to work as best as possible, even with slight disturbance, it still should be able to work. But if it's outside, then it's a different issue. But it has to be a slight robust. And this is the real test of the AI controller in the real world. Okay, in simulation, it's a different issue. It's not too difficult to make it work. But for the real online, where you have the real test, that's the real test of a controller, when it can be able to handle different noise, different disturbance that comes into the system. Although it has been trained, but it depends on the sort of noise and disturbance that you see coming to the system, and the model mismatch that you expect within the actual system itself. Okay, so in control application chemical process, you can have the simulation side and online. There are a lot of it have been implemented mainly in simulation, very few online. And some of these are mentioned here in this presentation. So there are a lot of methods that are being used using direct inverse, predictive, adaptive that I mentioned, to GPC, and so on, for different objectives, temperature, level, and so on. Different systems, semi-batch to tank, bent tank pressure, and so on. Typical chemical process systems using different types of neural network, multi-layered sigmoidal, and so on. These are the specification for the neural network structure. And also for mostly will be set point and disturbance, but some may be for disturbance. But this is all some of the papers very long time ago, since 1992. It's been used. As I say, most of these simulation, but we have an online one. Here, the one that we have done in 1996, we did an online system test, and but again, it's in a pilot plant system that we use it, so it's still not yet fully implemented in the real world because of the problem of robustness that we have to face when we use neural network, AI controllers, and so on. But anyway, it's been there for some time in many systems. And if you these are different predictive control strategies I mentioned to you initially. Again, different types of objective we have. So many usage can be used, so many different systems, different types of neural network, different robustness, set point, disturbance, and so on. That has been tested using these different types of different neural network. But mainly, this is the neural network used in predictive control. So now there's more work on this in the MPC, where using MPC, but mainly using the neural network as the model within the MPC system. So this is also common usage for neural network nowadays using neural network models in MPC. MPC have different type of models, and this is one of them that you can use AI for some of the model of system that is very difficult to be able to model using real world, using the normal first principle. Okay, in inverse model controls, again, you can use the IMC or the direct inverse for different composition, temperature, different system, different type neural network, and different robustness. Has been used extensively in all this, mainly in simulation, as I told you. Again, also it has been used for in adaptive control strategies. Yes, again, also in simulation, we have different types of adaptive. It's online adaptive, it's one online adaptation. As you're running it, you adapt the neural network model for product consumption, for CSTR fermentation, and so on. And different type neural network, different models. As you can see, most of its systems are difficult to model using first principle. Because first principle, it seems to be linear and easy to be modeled, then there's no issue of using PID or PID conventional methods. But systems are difficult to model, highly nonlinear system, then this is where you use AI and advanced control methods to take advantage of its ability to be able to model nonlinear mapping. And this, you can see most of it are quite difficult to model using straightforward model system. A lot of them are nonlinear system and fermentation and so on. So neural network has been proven that it can be used in all the system quite effectively for chemical process systems. These are actual online application that has been used mostly on the lab scale and also some pilot plant using the direct inverse, predictive, adaptive, uh, the embedded controllers, the GPC, predictive control methods, inferential methods, okay, the GMC, generic model control, and so on. Different methods that we've thought about the non-linear system, non-linear system, but using neural network as some of its model. Okay, with different control objectives to control temperature, level, pressure, and so on. Okay, standard chemical process systems that we normally see, and in a different sort of system, which you can see are very highly nonlinear, semi-batch, furnace, okay, stabilizer, plant, semi-batch reactors, tubular neutralizing reactor, very highly nonlinear, packed with reactor. We have a polymerization reactor, very highly nonlinear, okay, partially simulated, and fermenters, and all these. So a lot of them are highly nonlinear systems. Some are slightly nonlinear, but many of them are highly nonlinear, which is where the neural network has given an advantage on them. And it's online. Whether it be pilot plant or be uh, on the lab scale, but it's still something that is has to be robust to be able to work in the real world. Using different types of neural network, we can improve on this neural network, but it doesn't really matter. But these are mostly the multi-layered and with different activation function on the middle or output layers. Okay, can be the same and so on. Recurrent, only one of few recurrence neural network. Okay, where you have feedback from the output to the input, and mostly, of course, set point is the main thing, but also you have disturbance and also you have optimal control and so on in online application. So this just to show some of the very robust, very wide range of usage using neural network in the control strategy. Whether the neural network is used just as a model itself, or used as a controller itself, or used both as a model or controller in different in the IMC method. Sometimes just model itself, like in the model predictive method. Sometimes model itself in the adaptive method. Sometimes using invert the model, inverse model, and the model in the direct adaptive method, or just the controller itself in the direct inverse control method, or using the model and the controller in the IMC sort of methods, strategies that we have mentioned before. But at the end of the day, what is important is that the neural network has to be robust to be able to cater for disturbances, model mismatch, some noises, after making sure that it works on the set point. On the set point itself, it's not that easy to work on using for nonlinear system, but after the set point, then we have to check for after the servo control method, and of course we have to check for its application in the regulatory or disturbance changes, where all controllers we have to go through the servo regulatory, and also to make sure it's robust, and we have to test it on the in the model mismatch and some noise in the real. When you have in the real world, of course, we have noise, so there's no issue. For simulation, we can introduce the noise to make it like a real world. But when we already have it on the actual online, then the noise is already inherent in the system itself, because all online systems have got noise in the signals coming in, so that's already tested. But and also the model mismatch is also there in online, and online system are the real test to make sure that the system is robust. Normally we test it using online system, because that is the real test that will show whether the system can cater for robustness and all these things, that and at the end of the day, that's where we're going to implement it online system in the real world, in the industrial world. First, of course, at the bench scale, and on the pilot plant, and then on the, so some of it have been implemented in the real world, but mostly neural network as the model, the predictive method. Forward, we call it the forward model. That's been used in the real world for online system. But neural network as an direct inverse controller in the online is not at the moment much visible yet, because of its difficulty in the robustness issue. If you if you work it on the training data, yes, it will work. If you have changes in the system operational, then we're not too sure yet. But of course, it can be done. But of course, the industries are not we're taking a risk. So what they do normally is they hybrid it with a model, or hybrid it with a PID and so on, to use neural network in a hybrid fashion. So that's also possible. And but in the future, it will be more on hybrid method using neural network AI with other methods, GMC methods, or hybrid with PID and so on. AI with the fuzzy or neural, and hybrid with others. So that's going to be the future for AI control methods in the real world, in the industry. In the simulation or bench scale, it's already tested, but on the real world usage, that is going to be the future expectation for AI-based methods, especially neural network, or the fuzzy and neural fuzzy also is possible. And if you have seen the fuzzy method, you've seen the neural network method, we can also combine neural fuzzy, which is also a robust method that can be used online. The only issue is whether it's going to be robust for different operating regions, and that leads a lot more research work to be done for researchers and academics in the universities. Okay, so that's